Okay, we're going to consider graphing simple harmonic motion, and first we will do it with respect to time, and then a little later spatially. So here's our position time graph, x versus t, and big T means period, so quarter, half, 3/4, 1 full period. Now it'd be easier to show you this visually with the actual system, but with my red cursor here, a little red laser beam, think of the object going back and forth in SHM, the horizontal spring mass system. So here's the equilibrium and it goes back and forth. So if we start here, which is the idea, go all the way to this side and back, that's a half a cycle, and then all the way through to the other side and back to the beginning, that's a full cycle. That's 1 period. So that's what we're doing. So if you observe the operation of this system, you'll notice at the beginning, so at the beginning we have 0 displacement, so we can put that data point there. There it is. Now at 1/4 period, it's all the way over to the end, right? 1/4, 1/2, 3/4, a whole. Are you getting a visual picture of that? Good. So in 1/4 period, it's all the way to the end. That is the amplitude. And then in the next quarter, it's back to the equilibrium again. So we'll graph that, plot that point. Those are big data points, yes. So you can see them. Here's the equilibrium, and at 3/4 of a period, we're all the way to the left. And then 1 period, we're back to the equilibrium position again. So there it is. Now we can repeat that. 1, 2, 3, 4. There, it's all repeated. Now if we were to add a whole bunch more data points in between the ones I plotted, what we would recognize is we have a graph. We would have a graph that looks like this, and like what you see here being mapped out. Now that has a very familiar look to it, doesn't it? Namely, it's a sine wave graph. It's a sine graph. So that's a very important kind of discovery we make when we plot the position with respect to time, is that it plots out as a sine curve with x being maximum at the ends, 0 in the middle. All right? Now I want to plot the motion, not the position. And to get the motion or velocity from a position graph, do you remember how we go from velocity to position? We did that earlier, and it was finding the slope or the derivative, if that is meaningful to you at this point. So here we have Vmax and negative Vmax, maximum values of the velocity or speed in the plus and minus direction. Well, at the equilibrium point, if you recall, by observation here at the equilibrium, you'll notice it's actually going fastest there. So at 0 point in time, we have maximum velocity. Then when it gets all the way to the end, it comes to a stop. So there's 0. And then back to the equilibrium point again. It's maximum, but it's going the other way. And then at 3/4 period, we notice it coming to rest again. And then back to the equilibrium. It's moving at its maximum velocity in the positive direction once again. So we can repeat this whole scenario again and again and again. And when we plot this carefully with more data points that aren't shown here, we see this quite familiar pattern showing again. It's not sine. In this case, it's cosine. So going from position to velocity, we went from a sine function to a cosine function, with velocity being the maximum in the middle and 0 at the ends. So there's a difference there. Okay, so we're seeing a pattern here, very important one, and now we're going to look at a couple other things like acceleration and then force. So acceleration time graph. We discovered a long time ago that to get acceleration from a velocity graph, which is the previous graph we just drew for this SHM, you just take the slope. So if you consider the slope of the line at every point, you will get the value of the acceleration. I didn't explain that very well in the previous slide. The position graph, if you take the slope at any point, you should see that it matches the velocity graph, and which gave us the cosine function. And also it makes sense in terms of spatially or positionally thinking about what the motion is of the SHM object at those various locations. So here as well, we have this object moving back and forth, accelerating max at the ends, right? Max this way and max this way. And what's going on in the middle? Is there any restoring force? There's no restoring force when it's right in the middle at the equilibrium position. So the acceleration will be 0. So that's what it is at the beginning then, 0. Now at 0.25 t, we're all the way over here. Now at that point, it's being accelerated toward the equilibrium position, and it's a maximum value of acceleration. So that's in the left direction is negative. So it's actually a negative acceleration. Now, does this match the value of the slope of the velocity graph? Yes, because the velocity graph at 0.25 t was maximally down. It was moving, it was like this. The slope was negative at the max value. So there is the value of the slope, etc. You can say that for every point here. The velocity graph at this location here was 0. The slope of the velocity graph was negative, but the value of the velocity graph was negative. The slope was 0, is 0. And there's no acceleration at the 0.5 period point. So 0.25, 0.5. You're back at the equilibrium, no acceleration. Then at 0.75, it's all the way to the other side and accelerating maximally to the right. And so that's a positive acceleration. And then back to the equilibrium where it's no acceleration again. And we can repeat this a second time. And so when we fill in the values with all the data that is there and is not there, we discover this nice trigonometric function again, which is minus sign. So negative sign. That'll be the slope of the velocity graph at every point as well. So A is maximum at the ends, 0 in the middle, and always points toward the middle. The acceleration always points toward the middle. Last one we'll do, let's check out force. So what is the force acting on the mass? Well, to find force from acceleration, you know what to do. You just multiply it by m. That's the proportionality constant, ma. M, which then is proportional to a, F equals ma. So we have plus and minus F max. So this, we should know that the force and net force and acceleration are in the same direction. Therefore, the shape of the graph down here should match the acceleration graph, just scaled by mass, the different physical quantity. No force at the equilibrium. At a quarter period, we got a maximum force pointing to the left, then 0 again, then maximum to the right, then 0, and it repeats. Just like that. So we can fill it in. And there is what the function looks like. Totally matches the acceleration. So F is maximum at the ends, 0 in the middle, and always points toward the middle. So that is an overview of the graph, the way that the simple harmonic motion graphs in time, position, velocity, acceleration, and then force.